lecture that is going to focus on proton NMR. So again, NMR is nuclear magnetic resonance spectroscopy. We'll talk a little bit about how signals are detected, how samples are made, how you analyze, and really, again, what C13 and 1H NMR relate to are the uniqueness concept. We're given a structure to determine unique number of carbons, unique number of hydrogen sets in the ratio. What you'll notice from today's lecture when we start looking at proton NMR is that it looks pretty different from carbon. Carbon NMR signals are just a line that come off the baseline. So really what you're doing is just counting. So as you count, that relates back to the uniqueness that you determine from looking at the structure. With proton, it's a little different. The signals don't look the same. And so there's this concept of multiplicity, why any one signal can have multiple lines. And then within the lines of that signal, the intensities of the separate lines. So there's a rational way of understanding this, and that's what we'll talk about in today's lecture. Any questions before we begin? So a little bit about terminology and the NMR spectrum. So the NMR instrument is basically a big doer. So if you have like a Stanley Cup or a Yeti or something, that's like a doer, right? It keeps hot things hot and cold things cold. So it has these surfaces, and inside there's a vacuum, and the vacuum is what sort of mitigates the temperature from the external part to the internal part. The NMR instrument is a big doer that's filled with liquid helium and liquid nitrogen that cool a copper wire to form a superconducting magnet. So you have a really strong magnetic field, and a magnetic field has a vector to it. A vector is something with a direction and a magnitude. If you could see the magnetic field, it would look like a donut. So it sort of goes up, over, and back around in 360 degrees. So the magnetic field is set, and what happens is the nuclei either align themselves with or against that magnetic field. And then you have this external radio frequency generator, and so the operating frequency is in megahertz. As you increase up from 60, 90, 400, 500, 600, basically what that's doing is affecting the resolution. And the easiest way to think about it is, look at your phone, and, like 60 megahertz would be like a phone from like 15 years ago, where the screen is really pixelated. Nowadays, these are like 4K screens or something. So basically, resolution is the number of, say, slices per 1 part per million on the spectrum. So we said the x-axis, the Greek delta D was chemical shift in parts per million. So for every 1 part per million, based on the operating frequency that you're at, you increase the resolution. And the reason that's important in proton NMR is the total shift is from 0 to 12. And so all the functional groups that you've learned lie within there. Remember, carbon was 0 to 220, so you have a much wider spread. What happens in proton NMR is you get functional groups overlapping, and it's harder to sort of suss out what belongs to what. But as you increase the operating frequency, you get better resolution. So again, we're not going to do too much math in this course with equations at least, but the chemical shift is the distance downfield from tetramethylsilane. So tetramethylsilane is this compound that's added as it calibrates the spectrum to 0 parts per million. So the distance downfield from TMS in hertz divided by the operating frequency in megahertz. So notice hertz divided by megahertz gets you parts per million. It's just a number. And again, we read this spectrum sort of opposite the normal way. You start at 0 and you read left. So it increases positively to the left. If you go the other way to the right, this would be -1. And so that's possible, but we won't really see that too much. Some old-timey historical terms. Again, it takes me 5 to 10 seconds to calibrate myself to these every time I'm talking about NMR, but towards 0 is called upfield. That relates to the field strength of the magnet. It's also called shielded, and it's the lower frequency. And so I have the Death Star being shielded by the force field here. And then if you go towards 12, that's called downfield. That's de-shielded, and it's higher frequency. All that means is the nuclei feel the external magnetic field more. What does that translate into? Along from 0 to 12 is where you're going to see your different functional groups, whether it's an alkane, an alkyne, an alkene, an aromatic hydrogen. How they interact with the field shifts them on that scale. So we ended last time with looking at the ester and the ketone. And we said there was 3 unique carbons, 2 unique sets of hydrogen, and they were in a ratio of 2 to 2. So we're at our proton NMR here. Here's 0 parts per million. Again, this is the chemical shift. So we have a peak at 2.94 and 4.18. So there's 2, right? And so it narrows it down for us because we already said the ratio has to be 2 to 2. And so what we're going to talk about again is if we sort of think about methane, CH4, now we're looking at the H's for proton NMR. We're going to say that's approximately 0 parts per million. And then any substitutions we do are going to shift it to the left. So again, that's the chemical shift, 2.94 and then 4.18. For the ketone, we said there was 4 unique carbons, 3 sets of H, which were 3, 3, and 2. So we see the 3 signals, right? Here's 1, there's 2, and then there's 3. Now what we want to dive into is we want to assign the hydrogens to those signals. And then the other thing that we're not sure of is, notice the numbers 3, 3, and 2. So what signal gets what ratio of hydrogens? So we're gonna learn about, as we substitute methane, how does that affect the chemical shift? And then, as we'll see in the next slide, which is a blow up of these spectra, the signals look a lot different. And how we interpret the way they look is going to help us sort of think backwards to how we can do the assignments. So let's focus on the ester. You see the two signals blown up. So there's the first one and then the second one. Notice how they look different than carbon now. So carbon was just a line. But now each of these has how many lines to them? If you ignore sort of the width and just maybe count the tops. So there's 3. So what I meant by that is, when you're reading it, this would be 1, 2, 3 lines. Whereas, again, a carbon was just 1 line. So the question that comes up is, why does it do that? Then the other question is, why is line number 2 larger than 1 and 3? The number of lines is called the multiplicity. And then we have this issue of the heights of those lines, or I'll say intensity. So roughly looking at this first signal here, can you say anything about the height of line 2 relative to 1 and 3, if you had to guess? It's about twice the size. So we would say it's a 1 to 2 to 1 ratio. And so the same for the other signal down here, has 3 lines, a 1 to 2 to 1 ratio. Now, if we look at the ketone, we have this signal here, a little past 1. That looks like what we saw already. But then we have this signal. It only has 1 line, right? So why is that different? And then the third signal has how many lines? 4. So what is going on here? How do we explain this? So you have 4 lines here. One line there, 1, 2, 3. So the number of lines is telling us something that we can use to help start building up the molecule. So if you didn't know that was if you didn't see that ketone up there, you could look at this data, think through the logic, and then piece it back together to arrive at that structure. If you had to guess about the ratio of lines 2 and 3 here are the same height, right? How big a difference do you think 2 and 3 are to 1 and 4? Huh? It's more than 2 times, that's for sure. I mean, you can count the little squares maybe. It's hard to see, but there's like a grid here. So this one ends up being uh, 1 to 3 to 3 to 1. So let me just write something and we'll see if it jogs your memory from years past. So if I start with 1, so that's row 1. Then row 2, I'm going to go 1 to 1. Row 3, I'm going to go 1 to 2 to 1. Row 4, 1 to 3 to 3 to 1. Does that jog your memory for anything you've learned in maybe a math class? That's called Pascal's triangle. And so it correlates to the number of lines that you see in a signal. So if you just see one line, that's what we see here. That's the intensity of that line. If you see 2 lines, they'll be equal in a 1-to-1 ratio. 3 lines, as we saw for the ester and for the ketone, it was 1 to 2 to 1. And then 4 lines, 1 to 3 to 3 to 1. Do you see how this triangle is constructed? The edges or slopes are always 1. So to get the middle number, you add sort of, you're going left to right. So there's 1, and this 2 comes from adding 1 plus 1, that equals 2. And then you go back to 1. You have 1, the 3 comes from 1 plus 2 equals 3, 2 plus 1 equals 3, and then 1. So just looking at any signal, you're counting the lines, and then the Pascal's triangle is telling you the intensity of those lines. And then it's further going to tell you something that we'll get to in about 10 or 15 minutes about how you use that information to construct the carbon H backbone of your structure. Before we get too much into that, the first thing I want to talk to is where on the spectrum you'll see these proton signals. And again, that's the chemical shift. The Greek letter delta, and it's reported in parts per million. So as we said, what we're going to do is think about methane at, we'll just roughly say 0 parts per million. It's a little bit more than that, but we're going to substitute off some other group. We'll say X. And then how does it affect the hydrogens that are circled in blue? So as you do each of these substitutions, it's going to move that signal around between 0 and 12. And so empirically, this is known as Schulery's rules. Do you know what empirical means? Empirical means you're just making observations, and then you can sort of set up a rule. It's not really theory-based. It's just these are the observations I've seen, like all bananas are yellow, something that you can see, and it's an evident fact. And so what people have done was just make different derivatives and see how that X group moves that chemical shift away from 0. So starting in the table here, methane we'll say is at 0.23. And then if we substitute an H, so H going to CH3, now again, what we're looking at is the chemical shift of the hydrogen atoms there. That's going to add this number here, 0.63 to the 0.23. And so you'll see those signals at 0.86. For the heteroatom series, we're increasing electronegativity. You can see that it's now going to push it, 2 or more parts per million past the normal methane chemical shift. And then as you go down for the halogens, that effect decreases because the atoms get larger, and as well the electronegativity also decreases. So really what you're trying to clue into when you read the spectrum is where you see a signal and how you can associate that with the functional groups you already know. So this table summarizes what we learned about C13 chemical shifts as well as the proton chemical shifts, and how these different groups affect either the C13 signal or the 1H signal. So again, to recap, where you're seeing the signal on the spectrum is telling you what functional group either the carbon or the hydrogens belong to. So what about the effect of multiple substitutions? So on this table here, if we're starting from methane over here on the right, so there's all hydrogens, there's one set, the ratio is 4. We're going to say the baseline is 0.23 parts per million. And then we're going to take one of those hydrogens and substitute it for the halogens. And again, what we're looking at is how do those hydrogens circled in blue move? So we know that fluorine is the most electronegative, and you can see that by substituting one fluorine, now those signals are at 4.8. Because electronegativity decreases, that effect is not as large. So what about if you take another H and you substitute for a second halogen? So we're looking at those two hydrogens. So 4.28 minus 0.23 is like 4.05. Notice the difference here, 6.62. So by adding that second halogen, it's not like 4.05 times 2, because that you would then expect to see that at 8. So overall, when you're adding more, the effect decreases. It's not sort of linear, where now I have 2 of these, it's adding in the same sort of fashion. And then you add 3 halogens, we're looking at that hydrogen, and you can see now the effect is even smaller, right? So it's the difference between those two is like 0.25. So the magnitude of that additivity rule falls off as you add more heteroatoms to the carbon. So that's looking at the effect only on one carbon. How does that influence the hydrogen shifts? What about when we have a chain of carbons? How does the heteroatom affect hydrogens at the next position, 2 or 3 or 4? So the chemical shift, that magnitude will decrease as you move away from the carbon atom bearing the heteroatom. So again, X here are your halogens. And what I've numbered 1, 2, 3, and 4. Again, these are the chemical shifts of the hydrogens attached to those carbons. And what you can see, the hydrogens on carbon 1 experience the greatest effect. When you move to the CH2 group on carbon 2, notice it's not as far. And then 4, which looks most like so that looks most like methane, but the chemical shift is 0.95. So the influence of that heteroatom all the way on carbon 1 is still affecting it. And the way that I think of this is it's like a tug of war. That halogen or heteroatom through the chain is pulling that chemical shift. And a way we represent that is like with an arrowhead on the carbon backbone. So through that carbon backbone, it's affecting the chemical shift all the way at the end of the chain. Question?
I don't exactly understand what the chart is saying. Whatever, 1, 2, 3, 4, does that mean you're adding it at each spot?
This is these numbers here, 1, 2, 3, and 4. That's just the numbering of the carbon atoms.
Right. So whatever you say that you're adding, wait, never mind, I got it. Sorry.
So here's the numbering. And then that's the chemical shift of those hydrogens. So in this molecule, I'll just draw the fluorine. So this would be called fluorobutane. And so each set of hydrogens is going to be unique. So that's what we're seeing here. 1, 2, 3, 4. That's the 4. And if we just sort of look at the ratio in order, 2, 2, 2, and 3. The hydrogens on carbon 1 occur at 4.49. These hydrogens, 1.52. Hydrogens on carbon 3, 1.34, and then the last methyl group, 0.95. So again, you're sort of looking at each individual situation, how has it deviated from methane, and then approximating what the chemical shift should be. I don't have a spectrum of this compound to show you, but it would show 4 unique signals. Yeah.
Is it common whenever you have a linear carbon chain like that for the unique hydrogens to be in a line?
So the question was, when you see these 4 unique sets, can you sort of assume that when you're reading it, you can just make like the assignments based on that heteroatom? I would say for the most part, I'm not a confident person, so I'm never 100% about anything. So I'm going to hedge my bets and say 90% of the time that sort of holds. But again, to sort of think that way, again, the way you draw the molecule is important, so that sort of maps onto how the spectrum would look. Any questions at this point? So we'll do the assignments of the ester and the ketone, and then we're going to look at why those signals have multiple lines. What is the thing we can use to predict that? There is a website at the University of Rochester called Not Voodoo, and it was created by a professor there to sort of demystify organic chemistry. I can very confidently tell you that everything we learn, you can rationally predict what's going to happen. It's not just whatever. There is reasons for why you see things at this chemical shift, why it looks that way. So let's sort of put that to practice. And we're basically asked to assign the hydrogens on carbon A and carbon B to their chemical shifts. So carbon A is bonded to a carbonyl group and a methylene group. B is bonded to a heteroatom oxygen and a methylene group. So the influence of that heteroatom oxygen should push it farther away from 0 than those on A. So the correct answer for this would be B. B. So these would be 4.18, and these would be 2.94. So again, that heteroatom is going to sort of rule the roost in terms of the magnitude of the chemical shift away from methane. So the ketone has A, B, and C. And I think we said last time that A is much different than B and C. And the reason for that is B and C are both bonded to that carbonyl, right? So B and C should be more clustered towards one another than A. Even though A and C both look like methane, the substitution of that carbonyl is going to influence it more. So A should occur at what chemical shift? 1.05. And so we can eliminate this and this, so that's C and D we can eliminate. So now between choices or hydrogens B and C, so these two, which one has more substitutions to it, B or C? So B has more substitutions, again, meaning it should be further away than C. And so I think looking at this, A is going to be the correct response. So 1.05, 2.10, or sorry, 2.39. What the hell am I doing? Okay, I can't erase that. Let me redraw it. Okay, I think that's right. A couple questions. I think I saw you first. Say it again. Yeah. What was your question? And your question?
I was going to ask why D was
So when we talk about substitutions, again, keep in mind for this, we're looking at those hydrogens. How does moving from this H and substituting it for an X group shift those hydrogens that are circled in blue? For this CH3 group, you've substituted that H for CH2. Now you have these two which are bonded to the carbonyl. This one's substituted for a carbonyl. So that's going to have a greater chemical shift than a CH2. This one at 2.39, you've now done two substitutions. You have the CH3 group on the left and then the carbonyl group on the right. So they're going to have different magnitudes of how they affect the chemical shift, but when you add them together, it's going to push it further than what this one would be. And again, that table of Schulery's rules, I just gave you an abbreviated one, but I mean, there's pages of different groups, how they affect the magnitude of that shift. So nowadays, like the spectra that you saw originally in the first couple of slides, I have an app on my phone that just generates these things. And the way it generates them, it uses these rules. So it's all in a computer program now, where it analyzes the structures, it starts with these starting points, and just adds these different magnitudes to each. So the question is, why do C13 and 1H signals look different? So again, C13 signals are just a line. So again, if this is the baseline, the signal goes up, immediately back down, and then baseline. However, we saw that proton NMR signals can have a single line or multiple lines. So there's a single line, you can see it goes up, and then it comes back down. This one has 4 lines, this one has 3 lines. Like, why is that? So another layer to the learning lasagna here is after you determine the uniqueness sets of hydrogen, you have to go one level deeper and now predict how each of those signals is going to look. So the reason that the spectra are different, as we saw with mass spectrometry, it has to deal with the isotope abundances of those nuclei. The other thing that's important is spin, and I'll just briefly comment on that. For this class, we either have a spin of +1/2 or -1/2. And if you visually want to think about it, it's spin up or spin down, or spin clockwise, spin counterclockwise. And again, that's just a tool in which we as humans think about what is happening. And so these are different spin states. So the C13 or the 1H can be in one of two spin states. For the isotope abundances, notice that this number here is odd, so C13 and 1H. So the number of protons plus neutrons must be odd for you to see the nuclei in NMR. For this class, we're only dealing with proton and carbon, so any other nuclei we're not going to talk about. So conceptually, this is where or why you see the differences in these appearances. We said that the C13 nuclei was only about 1% abundant. And again, that is what the experiment is observing. Proton is 100% abundant. So now the issue is the nuclei can be in one of two spin states. So what happens is if you're looking at a specific carbon or its attached hydrogens, the signal that you see is influenced by the neighbor. So like Autumn down here has, in her row, like no neighbors next to her. And so she would appear as a singlet in the NMR. Oh, I forgot your name. Chloe. So Chloe has one neighbor. So she would appear as a doublet in the NMR. And so there's just a simple rule, we call it the neighboring group rule, to determine the number of lines. So the reason that carbon only occurs as like a line is because due to that isotope abundance where it's only 1%, really what you're seeing in the bulk sample is a mixture of compounds where that C13 is located on the different carbons of the chain. So in this spectrum, you see 1, 2, 3, 4 signals. But in the bulk solution that's measured, for example, this carbon, the sp2 hybridized carbon, you're only seeing it when that C13 is there. Then for the other three, you're seeing it when it's in the other positions. So no one molecule in carbon-13 is going to have all of the carbons as C13. That's like almost a statistical anomaly for that to happen because of that isotope abundance. So it says I don't even know if this math is right. I'm not a mathematician. But the odds of having two carbons next to each other, that's pretty low. So since we don't see that, the signals only look like lines. Now, the reason that proton NMR is a little bit more complicated to interpret is because that nuclei is essentially 100% abundant. So each hydrogen can either be plus 1/2 or minus 1/2 in the spin state. And so basically the nuclei you're interested in is affected by the neighboring nuclei spin states. So that is what leads to this change in the peak shape. So I've labeled, this is the methyl group, A, CH3. B is the methylene, CH2. And then C is the other methyl group. And so, again, that's a ratio of 3 to 3 to 2. That's what you can do visually in terms of the uniqueness. If this signal has 3 hydrogens, why does it occur as one line? Whereas this is also 3 hydrogens, but now it's 3 lines. The CH2 group is 4 lines. Can you make sense of that looking at the structure at all? So if we look at C, C is the simplest one, right? Because it's one line. It's a CH3 group. So do your first approximation when you're determining your uniqueness, sort of everything is one line. Then when you go down to the next part of the analysis, you're going to see, is that going to change from a single line? CH3, that's a neighboring carbon, right? There's only one neighboring carbon. There's no hydrogens on it. If we look at A is 3 lines. It's a CH3 group. It has one neighbor, B. How many hydrogens are on that neighbor? 2. How do you go from 2 to 3? Plus 1. So it's called the N+1 rule. So look at now B. B has 2 neighbors. The carbonyl that has no hydrogens. The methyl group has 3. And then how many lines do you see there? 4. So it's called the neighbor group rule. So you count the total number of neighbors, you add 1. That's going to get you the number of lines in that signal. So again, this is where you have to keep things straight in the following sense. So again, B has 4 lines. The 4 lines of B are determined by the neighbor A. So if you did not see this structure and you looked at that signal and said, okay, it's 4 lines, Therefore, whatever is attached to it has to have a total of 3 hydrogens. So we've run through this sort of already, the number of lines in each signal. So A has 3 lines, C has 1, and B has 4. So again, keep in mind, that's the total signal. And then that's the number of lines as we count them. So signal A has 3 lines, B 4, C 1. And so we call the number of lines, again, the multiplicity. And so each unique signal has a name. So 1 line is called a singlet. 2 lines is called a doublet. 3 lines is a triplet. 4 lines is a quartet. There are situations where you'll see like 5, 6, and 7, but overall those are sort of unique, and we'll explain those circumstances in which they arise. So we have so S, D, T, and Q are the abbreviations. So a triplet, a singlet, and a quartet. The other thing about the next layer down in this circle of Dante's hell we're traversing here, so that would be my drawing of a triplet. We said it was a 1 to 2 to 1 ratio. The other thing we'll talk about is this distance here between the lines. And that's called a coupling constant. So while I'm thinking about it, because A and B are neighbors, the quartet is coupled to the triplet, and the triplet is coupled to the quartet. So it's a reciprocal relationship. So for example, this group here, CH2, CH3, that's 2 carbons. It's an ethyl group. An ethyl group will always have a quartet and a triplet. So as you see these different sort of smaller fragments that are common within molecules, they'll have unique signatures in the proton NMR. So when you see a singlet, what that's telling you is that the neighbor, there's no hydrogens on the neighbor. It's not necessarily telling you the total number of hydrogens to that signal. It can be 1, 2, or 3. That's what you get from the uniqueness ratio. So we said signal A belongs to CH3, and again, the 3 is the ratio there. There's 3 lines in the signal, 1, 2, 3, and then that's called a triplet or T. B is a CH2 group, so the ratio there is 2. There's 4 lines, 1, 2, 3, and 4. So that's a quartet or Q. And then C was the other methyl group. It has 1 line, so that's called a singlet or S. So a word that I'll use to determine how multiplicity arises. Again, your first approximation is that everything is a singlet. Then you look at the neighbors to see if there's, you apply the n+1 rule, and then you're going to see if that singlet is then split by the neighbors. So multiplicity results from splitting. And why that happens will probably be Wednesday or Friday when we talk more about spin states. Again, because the question we still want to answer is, in this ratio here of 1 to 2 to 1, why is it that ratio? And again, that relates back to the spin states of the neighbors. So we determined that the rule we used was called the n+1 rule. If we're looking at signal A, so signal A is a CH3 group. It only has neighbor B. That has 2 hydrogens on it. So n+1, 2 plus 1 equals 3. So same analysis for signal B, that's a CH2 group. The neighbor is A, that had 3 hydrogens. So 3 plus 1 equals 4, so triplet, quartet, and singlet. So you need to be able to, look at those number of lines and then convert it into the multiplicity. So this table here just fills in that information for you. So number of lines going to the multiplicity M. So in the last minute here, we'll just wrap up on this slide. Again, when you're determining multiplicity, that's your second approximation that you're doing by looking at the number of neighbors, then using the n+1 rule to determine the number of lines. So that gets you lines in the signal, what it should look like, and then these are the abbreviations. The line here is about singlet, doublet, triplet, quartet. Those are the most common. When you get below that, notice you have a lot of neighbors, and then things increase. That gets kind of rare. And so we're going to delve deeper into that and really looking at as well the line intensities from that Pascal's triangle. And then ultimately coupling constants. So there's a lot more we have to interpret with proton. So we'll wrap up on that today. Don't forget to do your quiz. That opens in right now. We'll see you Wednesday.